All right, everybody, welcome back. So after our quick introduction to parametric surfaces in space, we will forge ahead now to the next and most important topic of the day today, which is surface integrals. So these are going to be just like line integrals. First, we'll do it to functions, and then later we'll talk about doing it to vector fields. So let's start with a surface in space that is parametrized by this formula, r of uv equals to x of uv in the first component, y of uv in the second component, and z of uv in the third component, where the pairs u and v vary over some region d of the uv plane. Now, I know we did a very quick introduction to this in the last video, so if you're feeling like you want more practice there, never fear. We will get more practice in this video and in some of the following videos. So just to recall, though, we had this kind of generic picture here where we had a nice rectangle in the UV plane, and the function r takes that rectangle and maybe warps it and stretches it or shrinks it, and anyway, then sits it inside of three-dimensional space, where it is now this kind of weird sheety thing that is the surface we call S. Okay? And so then, just like the idea of line integral of function, a surface integral of a function is going to come about from letting f of x, y, z be some function on space that we restrict to living over the surface S. And then we'll think of the surface S as sort of the analog of the kind of base xy plane over which we're going to want to do some kind of double integral of the function f over the surface S. But because that's kind of awkward since S is a two-dimensional thing sitting in three-dimensional space, to do a double integral of sorts over it, we will yank back here and instead do an honest double integral over the region D of the UV plane. But now when we do that, we're going to have to take into account how this function, little r, warps the sort of area of regions of D when it takes it into regions of S. Okay, and so there's a little bit of formal nonsense that we have to do to take care of that, and then it will kind of be built into our formula from there on out. So the first thing we'll do is break this region D into small little rectangles, right? The idea being that we're going to maybe try to approximate with some Riemann sum, although I'm not going to write the Riemann sum on these slides because we've got a lot to do today. So we'll break the region D into small little rectangles, and let's call their width delta U and their height delta V. Okay? And let's look at how the function r takes these rectangles into S. Well, I don't know how it takes it in there because we don't know anything about this function r, but we can maybe sort of theoretically approximate the image of those rectangles in S with maybe not rectangles on the nose, but maybe parallelograms instead. And that'll be good enough for our purposes. So the way that we'll do that is as follows. So at each point, r of uv that lives on the surface S, we have two sort of canonical tangent vectors that are handed to us by this function itself. One is called r sub u, which his components as a vector are the derivatives of the functions x of uv, y of uv, and z of uv, all just with respect to u. So it's kind of saying, like, how are you moving in S as you move just in the u direction back in D? And similarly, we have this other tangent vector, which is called r sub v, and its components are the derivatives of the functions x of uv, y of uv, and z of uv. But now those derivatives are taken just with respect to v. And so again, this guy tells us how you move tangentially along S just as you're moving directly in the v direction back in D. Okay, and so then those two vectors, r sub u and r sub v, they might not be exactly like perpendicular to each other like the sort of u direction and v direction are back in the region D. they might not any longer be perpendicular when they're moved into S, but they'll still, if R is a good enough function, which is like what all we're going to consider in this course, these two vectors will still form maybe a parallelogram of sorts, okay? And so we'll use those parallelograms to approximate how the function R takes those small rectangles in D into the surface S. So in particular, we'll take these tangent vectors R sub u and R sub v and just rescale them by the small little widths and heights of little rectangles that we've used to approximate, to approximate the region D with. And so then we'll make these small little approximating parallelograms over approximating the region S, okay? And so then what are going to be the area of those parallelograms? Well, if you hearken back to way long ago in like chapter 12, the beginning of this term, the area of parallelograms spanned by these two vectors is going to be the cross product of these two vectors. But now here, since each one of these vectors is really just scaled by some other constant delta u and delta v, we can yank those scalars out of our cross product and then take the length afterwards. So we've got that the areas of these parallelograms will then be the length of the cross product Ru cross Rv times these two scalars delta u and delta v. Okay, so now if those form the little approximating parallelograms that will form the sort of like base of our pieces for our surface integral, then the height of the pieces that go into our surface integral will just be the whatever function is that we're given evaluated along the surface. So then let's suppose we have that function f of x, y, z. And so we could form some kind of Riemann sum that's given to us by the area of those base parallelograms times this function. And then maybe, so it's really that Riemann sum would be given by the adding all those all those volumes up now, right? Area of base parallelogram times function value would give us some kind of volume of maybe some kind of prism of sorts. And we could add those up and get a Riemann sum to approximate our surface integral of a function. But then taking the limit of that would then ultimately give us the integral that we want on the nose. So we'll restrict f to this surface by considering the function what we call f of r of uv. That's all that is really saying, to restrict f to the surface. And so then the surface integral that we get is defined by the double integral over d of f of r of uv times this length of this cross product ru cross rv, because that gives us the sort of area of those base parallelograms that we use to approximate the surface S. So this is almost this is actually very much analogous to the way that we do double and triple integrals when we do a coordinate change. It's like here we're doing a coordinate change to u and v, because those are the essential data that we need to talk about objects that are defined over our surface. So when we do that, we have to wonder about how the parametrization at hand warped areas from the UV plane onto the surface S. And so how does it do that? Well, it does it in that warping of area by the length of this cross product here. So that's analogous to the sort of Jacobian matrix determinant from coordinate change conversation. And so the formal notation for this thing, the surface integral of f over s, is just this nonsense on the left here. So the actual computational data is what's over here. We'll do an honest double integral over the region D of the UV plane of this function here. And this factor here of the length of RU cross RV, that's always included when we do this. Again, for the same reason that it would be when we do a coordinate change. Okay, so that being said, if we put the constant function 1 on our surface, then that surface integral will actually compute the surface area of the surface S, which is great. So let's record that fact here, that the area of S, if S is parametrized over the region D of the UV plane by the function, say, R of UV, then the area of S is the double integral over D of the length of the cross product RU cross RV. So that is inherently in here is the constant function 1 multiplying that. Okay, so let's do an example with that. So let's let S be the portion of the cone z equals to the square root of x squared plus y squared between z equals 0 and z equals 4. So I've drawn that here, where I guess it's sort of implied that we cut this off at this height, and that's height z equals 4. Okay, so the first thing we're going to need to do this surface integral to compute the surface area of this cone is a parametrization for the cone. And that's most of the time is the most awkward and difficult and just kind of new thing for y'all to kind of climb over. And so one of the parts about it that's particularly awkward is that there's not just like one correct choice. One has a little bit of freedom here. And so we're going to kind of take our time now with that freedom and maybe take our first guess and then maybe tweak that guess to maybe be a nicer parametrization in this example. So the first guess that I could make, just going from the last video, is that this cone is the graph of the function z equals to the square root of x squared plus y squared. And if we look at this graph, what is the region of the xy plane over which we're graphing this function? We are going to restrict because we're going to stop off here at z equals to 4. And so if you were to stand higher up on the z-axis and stare down at this surface, the projection you would see in the xy plane would just be this circular disk of radius 4. So this radius is going to be 4, the same as the height that comes up here. Okay? And so the region of the xy plane over which we're really looking at the graph of this function is just the circular disk of radius 4. So let's keep that in mind too. So since we have the graph of a function, though, we can use the trick that we learned, the general example from the last video, where we can parameterize this surface using the coordinates x and y, right? So we'll have r of xy equals x in the first component, y in the second component, and then z will equal exactly that function of x and y, the square root of x squared plus y squared. Okay, so this is one choice. This is the first choice that we should probably think to make, since I kind of harped at you that whenever you have the graph of a two-variable function, this is an option that you have to parameterize your surface. Okay, but our region D here is the disk of radius 4. It's a disk, so we don't really like to use rectangular coordinates x and y to integrate over disks, right? Instead, we like polar coordinates. So let's maybe take this parameterization that we have here and change it into polar coordinates, because that way the region D will become in the sort of polar plane a rectangle, right? Remember, a disk was a polar box. So we'd rather integrate over something like that. So let's do it. And now, since we're already using the letter R in this context, and I don't want to be confusing and say it to mean two different things, I'm going to change this expression into polar coordinates, but I'm not going to use the polar coordinates r and theta. Instead, I'm just going to use the generic other coordinates u and v. So in particular, I'll let u take the place of r, and I'll let v take the place of theta. So that way, x becomes not r cosine theta, but u cosine v, okay? And y similarly becomes u sine of v, okay? And then x squared plus y squared becomes what? U squared. And so the square root of that becomes just u. So now we have a new parameterization just translating this old one into polar coordinates. And I think I like this one a little bit better, right? There's no square roots involved anymore. And I know now the region of the UV plane that goes into this is really a rectangle where u varies from 0 to 4 and v varies from 0 to 2 pi. That's much easier to deal with. So, okay, so now that we've got that, I think we're going to need probably those tangent vectors, r sub u and r sub v. Those are given to us as follows. R sub u, this is derivatives with respect to u, so we get cosine v, sine of v, and 1. And the derivatives of that function r with respect to v are given by minus sine u, or sorry, minus u sine v, u cosine v, and 0. Okay, so now let's take the cross product of these two. Let's see, in the first component, we'll get minus u cosine v. In the second component, we'll get minus u sine v. And in the third component, we get u cosine squared v plus u sine squared v, which is just u. All right, so now we need maybe the length of that cross product. So let's take its length. So its length is the square root of u squared cosine squared v plus u squared sine squared v plus u squared. So the first two terms go together. You can factor out a u squared and get that you have u squared times cosine squared v plus sine squared v, which is 1. So then you really have u squared plus this extra u squared, which gives you 2u squared underneath the radical. And so that one simplifies to the square root of 2 times u. Okay, so now then, now that we've got all the sort of essential data, the area of that cone, then the surface area of that cone is given to us by the double integral over the disk of radius 4 in the xy plane, centered at the origin. So in polar coordinates, that integral is from 0 to 2 pi in v land, and from 0 to 4 in u land. And so what do we get then? Let's see. So the first one, we'll have u squared over 2, right? And 4 squared over 2 is 8. So we get 8 square roots of 2. And we'll integrate that one from 0 to 2 pi and get 16 pi times the square root of 2. All right, so definitely a lot of moving parts in this, but you just kind of got to take it piece by piece and kind of follow your nose from there. Definitely the most awkward thing should be coming up with these parametrizations. And so in the next video, we'll make it a little bit harder and build up how we're going to do surface integrals of vector fields instead of just functions. So we'll see you then.